Okay, so this is problems 3 and 6 for group project 3. So problem 3 asks to evaluate the integral of e to the x over x dx as an infinite series. So I noticed there was a common power series. So e to the x actually equals the summation of 0 to infinity x to the n over n factorial. And I noticed that it wasn't just e to the x, it's e to the x over x. So e to the x over x, if we want to find that power series, we want to divide whatever we got for e to the x and just divide it by x. So we have e to the x over x equals the summation of 0 to infinity 1 over x times x to the n over n factorial. And if we divide these numbers, we get x to the n divided by x, which is x to the n minus 1, and then 1 over n factorial, which is just the same, 1 over n factorial, and 1 will be the coefficient here in front of the x, so nothing really changes. So we have e to the x over x. Since we divided by x, we got the summation of 0 to infinity x to the n minus 1 over n factorial. Now, the second step is I wanted to evaluate this integral. So the integral of e to the x over x dx, sorry, I'm talking kind of fast. We're actually going to plug what we found here from above into the e to the x over x. So we just plug that in here. So we'll have the integral of the summation of 0 to infinity and then x to the n minus 1 over n factorial dx. And so I wanted to shift the index to n equals 1 because I noticed that when you plug in 0 versus when you plug in any number more than 0, for example, 6 or 7 or 4 or 5, whatever, you'll notice that when you plug in n equals 0, the pattern is much different, or the number is much, much different than when you plug in n equals 6. So I wanted to change the index to n equals 1, and so I will take n equals 0, I'll plug in n equals 0. So when n is equal to 0, you'll have x to the negative 1 over 0 factorial, which is just 1 over x. So I took that integral separately, and then I started the index at 1, if that makes sense. So uh, we have integral of 1 over x dx plus the integral of the summation of n equals 1 to infinity x to the n minus 1 over n factorial. And notice how since I shifted the index, I didn't really change anything here. And so we're just going to evaluate these two. So first we'll evaluate this one, the integral of 1 over x dx. It's not too bad. It's just the natural log of the absolute value of x. And so when we are evaluating this second part, so since we're adding the integral, the summation of 1 to infinity x to the n minus 1 divided by n factorial, we're going to take this summation out because that's just a general rule. You can do like a property. So we have the integral of e to the x over x dx equals the natural log of the absolute value of x, because I got that from the 1 over x. So I just plugged that down here. And then I took the summation out. So plus the summation of 1, n equals 1 to infinity, and then the integral of x to the n minus 1 over n factorial dx. And so I just drop down the natural log of the absolute value of x down here, drop down the summation when we're adding it, and then I took the integral of this right here. Sorry, not the summation. I didn't mean to kind of circle that with my mouse. I took the integral of x to the n minus 1 over n factorial, and I got x to the n over n factorial times n. And so what I was going to reiterate from this lecture is, or from one of the lectures that our professor showed, you can see that the integral of f of x dx, there's a constant c. So I made sure I added that towards the end. And so I got the integral of e to the x over x dx is equal to the summation of n equals 1 to infinity x to the n over n factorial times n plus the natural log of the absolute value of x plus c. And so that is the infinite series for the integral of e to the x over x dx. So yeah. Now, if we move on to problem 6, asked to find the Taylor series for f of x equals 1 over x squared centered at a equals negative 1. So since it's centered at a equals negative 1, it will be x minus a. If you could see it like down here, it will be x minus a. And so x minus negative 1 is just x plus 1. So that's why I had x plus 1 around here. So let's ignore that really quick. So the first step we're going to do here is we're going to take the derivatives and we're going to plug in the values. So, or value, as I should say, since there's one value. So if we're not taking the derivative, just the normal function of f of x, that equals 1 over x squared, and you can rewrite that as x to the negative 2. And if you plug in negative 1, you'll simply just get 1. because 1 over, negative 1 squared is just 1 over 1, which is just 1. So I hope I didn't have to explain that very well. But so we took the first derivative, second, third, and fourth, and then once we got those derivatives, we rewrote them all here to kind of make it simpler in two ways. Just, you could choose which one to how you want to evaluate it. And we plugged in -1 for each derivative we took. So for example, take this one right here. So the derivative of f of x is just or the derivative of 1 over x squared is simply just -2 x to the -3, and we rewrote that here, and then we plugged in 1 and got 2, and then we did that for each derivative, like I said, and I got 1, 2, 6, 24, and 120. So I plugged in all those values, got the derivatives, all that, and then you can see a Taylor series is represented by f of x equals the summation of 0 to infinity f, and then the n represents the whatever derivative you're taking. So the first derivative, second, third, times a, which is what it's centered at, over n factorial, times x minus a to the n. And I'm going to reiterate what I said again. So since the center is -1, it's going to be x minus -1, which is just simply x plus 1. And then that will be the Taylor series. So that's just a general Taylor series. So I plugged in each of these values. So I did the normal function. We plugged in 1 in the normal function over 0 factorial because this is the 0th term, and then times x plus 1 to the 0. And we did that for every single one, as you can see the pattern. And when I plugged in the values, this is what I got. So 1 over 0 factorial plus 2 over 1 factorial times x to the x plus 1 to the first. And then I did that for each and every single one here. So for example, let's take the third derivative. So the third derivative of f of x is, oh, I did not mean to put 4 little parentheses right here. That just meant to be 3, so sorry about that. That's 24. So the third derivative is 24, so I got 24 over, and then since it's the third derivative, it's the third term, so it's 3 factorial, and then we have times x plus 1 to the third. So we did that all right here, and then we got this pattern right here. So 1 plus, or after I simplified it here, I got 1 plus 2 times x plus 1 to the first plus 3 times x plus 1 to the second, and so forth. And then I noticed this was simply an easy power series to come up with. You'll notice that you're simply just adding 1 to the coefficient, so I just did 1 plus n, fairly simple, and then the x plus 1 is going to stay constant, so x plus 1 to the n. So yeah, that is the Taylor series for f of x equals 1 over x squared centered at x equals -1. So yeah.